Today we are going to discuss physical properties of alkyl and aryl halide. So let's read from the book. Alkyl halides are colorless when pure. However, bromide and iodide develop colors when exposed to light. Many volatile halogen compounds have sweet smell. Now come to the first physical property, that is melting point and boiling points. Methyl chloride, methyl bromide, ethyl chloride and some chlorofluoromethanes are gases at room temperature. Higher members are liquid or solids. As we have already learned, molecules of organic halogen compounds are generally polar. Due to greater polarity as well as higher molecular mass compared to the parent hydrocarbon, the intermolecular force of attraction, dipole-dipole and van der Waals force of attraction are stronger in halogen derivatives. That is why the boiling point of chloride, bromide and iodides are considerably higher than those of hydrocarbons of comparable molecular mass. The attraction gets stronger as the molecule gets bigger in size and have more electrons. The pattern of variation of boiling point of different halides is depicted in figure 6.1. For the same alkyl group, boiling point of alkyl halides decreases in order. Alkyl iodide has higher boiling point than alkyl bromide. The alkyl bromide has higher boiling point than alkyl chloride, and alkyl chloride has higher boiling point than alkyl fluoride. This is because of the increase in size and mass of halogen atom. The magnitude of van der Waals force of attraction increases. Now let's see figure 6.1. There is comparison of boiling point of some alkyl halides is given. The first one is given methane halide. Red one is for chloride, blue one is for bromide and yellow one is for iodides. So when you observe the figure, here it is given if the molecule is chloromethane or bromomethane, they will be gases. In the second set of molecule, this is ethyl halide. So when you see, if the molecule is ethyl chloride, it will be gas. In third set of molecule, this is propyl halide. In propyl halide, this is chloride, bromide and this is iodide. These molecules may be liquid at room temperature. Now let's try to understand the meaning of these lines. As we have discussed in the previous video, the alkyl halide or aryl halides, they are polar in nature. That's why they have dipole-dipole interaction. So in the molecules of alkyl halide or aryl halide, they have dipole-dipole interaction in addition to the van der Waals force of attraction. Boiling point or melting point. They are directly proportional to the force of attraction between the molecules. If the molecule has a stronger force of attraction, they will obviously have higher melting point or boiling point. And in case of alkyl halide, if you compare between alkyl halide and hydrocarbon, in case of hydrocarbon, the molecule is non-polar. So hydrocarbons are non-polar. While alkyl halides, they are polar molecule, as we have discussed in the previous video. So they are polar molecule. In non-polar molecule, which is hydrocarbon, they have van der Waals force of attraction. They have van der Waals force of attraction. But in case of polar molecules, in addition to van der Waals force of attraction, they have dipole-dipole interaction. So there is one addition force of attraction in case of alkyl halides. That's why alkyl halides have higher boiling point as compared to hydrocarbon of comparable molecular mass. There is one more factor that affects the melting point and boiling point. Melting point and boiling point are directly proportional to the molecular mass. And bigger molecules have higher magnitude of van der Waals force of attraction. So we can establish a relation between molecular mass and van der Waals force of attraction. Bigger molecules have a stronger van der Waals force of attraction. So if the molecule have higher molecular mass, they will have more van der Waals force of attraction. So they will have more van der Waals force of attraction. So that's how you can say bigger molecules have higher van der Waals force of attraction. That's why they will have higher melting point or boiling point. That's why it is written here. Increase in size and mass of halogen atom, the magnitude of van der Waals force of attraction increases. So when you compare different alkyl halides having same alkyl group. So when you compare the boiling point of different alkyl halide having same alkyl group. So when you compare between different alkyl halides. So this is RF, RCl, RBr and this is Ri. In all the alkyl halide, alkyl group is same, but the halide group is different. This is fluoride. Fluoride is smaller than chloride. Chloride is smaller than bromide and bromide is smaller than iodide. So when you compare their molecular mass, so here alkyl chloride have higher molecular mass than alkyl fluoride and alkyl bromide has higher molecular mass than alkyl chloride and alkyl iodide have highest molecular mass among all of them. So that's why when you compare the van der Waals force of attraction. So when you compare van der Waals force of attraction, you will get the same trend in the magnitude of van der Waals force of attraction. That's why when you compare the boiling point, you will get again the same trend for the boiling point as well, because all these properties are proportional to each other. Now let's read from the book. The boiling points of isomeric haloalkanes decreases with increase in branching. For example, 2-bromo-2-methylpropane has the lowest boiling point among 3 isomers. Here there are 3 different isomers of bromobutane are given and their boiling points are given. So when you compare the boiling point of these 3 isomers of bromobutane, first isomer, it is normal bromobutane where there is no branching. Its boiling point is given 375 Kelvin. The next isomer is 2-bromobutane. Its boiling point is 364 Kelvin and the third isomer is 2-bromomethylpropane. Its boiling point is 346 Kelvin and it is the lowest boiling point among them. So as it is given here, boiling point of isomeric haloalkane decreases with increase in branching. Means if the molecule have more number of branches, its boiling point will be less. Now let's try to understand how branching decreases the boiling point. So when you draw the structure of 1-bromobutane, 1-bromobutane. Now draw the 3D structure for 1-bromobutane. So this is first carbon, second, third and this is fourth carbon and it is bonded to bromine. Each carbon is sp3 hybridized carbon. For sp3 hybridization, geometry will be tetrahedral. So when you draw tetrahedral geometry in 2D, so this is front bond and rear bond and again this is front bond and this is rear bond. Similarly here this is front bond and this is rear bond. So here that's how you can draw 3D geometry in 2D. When you try to pack such two molecules, they may get in contact with each other. Now draw the second isomer. This is 2-bromobutane. First carbon, second, third, fourth. There are 4 carbons and this bromine is bonded to second carbon. So here there is bromine. Now draw front bond and this is rear bond. And here maybe bromine is bonded to front carbon. So there will be rear bond. Now draw third isomer. This is 2-methyl 2-bromopropane. So this is 2-bromo 2-methyl propane. first carbon, second, and this is third carbon. And here there is front bond and this is rear bond. To front bond, CH3 is bonded and and bromine is bonded to rear bond. So this is 2-bromo-methyl propane. So if you take two molecules of each, if there is less branches, there will be more area of contact between the two molecules. But the branches decreases the area of contact between two molecules. There is one branch of bromine, while in case of third isomer, there are two branches. So branches create hindrance for the close packing of the molecules. If there are more branches, there will be less area of contact between the two molecules. And if there are less branches, the molecule can be packed closely and there will be more points of contact. There will be more points of contact. But if there are more branches, there will be less point of contacts. So there will be less points of contact. And if there is less point of contact, there will be less van der Waals force of attraction. So there will be less van der Waals force of attraction. And if there is less van der Waals force of attraction, its boiling point will be less. So boiling point will be less. And if there is more area of contact, there will be more van der Waals force of attraction. So here there will be more van der Waals force of attraction. As there is more van der Waals force of attraction, its boiling point will be high. So that's why the boiling point of normal bromobutane is higher than that of 2-bromobutane and it is higher than 2-methyl 2-bromopropane. Boiling points of isomeric dihalobenzenes are nearly same. However, para-isomer are high melting as compared to their ortho and meta-isomers. It is due to symmetry of para-isomer that fits in the crystal lattice better as compared to ortho or meta-isomers. So in case of dihalobenzene, in dihalobenzene, melting point depends on the symmetry. Symmetrical molecules have higher melting point. So here when you examine the boiling point of different isomers of dihalobenzene, the first one orthochlorobenzene, the second is metachlorobenzene and the third one is parachlorobenzene. So when you compare the boiling point of these isomers, it is nearly same. Orthochlorobenzene is 453, metachlorobenzene is 446 and parachlorobenzene is 448. So they all are nearly same. But when you compare the melting point of these isomers, there is a huge difference in the melting point of para-isomer. Para-isomer has highest melting point, it is 323 Kelvin. While the ortho and meta-isomer, they have nearly same melting point. For melting point, the reason is given. For para-isomer fits in crystal lattice better as compared to ortho and meta-isomer. And for the melting of the molecule, you require to break the crystal lattice. If it fits better in the crystal lattice, it will require more energy to break the crystal lattice. That's why para-isomer have higher melting point as compared to ortho and meta derivatives. Now come to the next physical property, it is density. Bromo, iodo and polychloro derivatives of hydrocarbons are heavier than water. The density increases with increase in number of carbon atoms, halogen atoms and atomic mass of halogen atom. Now let's compare the density of different haloalkanes. First one is normal chloropropane, second one is bromopropane and third one is iodopropane. When you compare the density of these isomers, chloro has lower density as compared to bromo and bromo has lower density as compared to iodo. Because the molecular mass of chloro, bromo and iodo They are in increasing order. Now come to the next molecule. It is given polychloro derivative of methane. The first one is dichloromethane, second is trichloromethane, and third is tetrachloromethane. On increasing the number of chlorine atom, density also increases. So tetrachloromethane has highest density and dichloromethane has lower density as compared to other polyhalogen compounds. So density also depends on the molecular mass. Molecule having higher molecular mass will have high density. The next physical property is given solubility. The haloalkanes are very slightly soluble in water. In order to dissolve haloalkanes in water, energy is required to overcome the attraction between haloalkane molecules and break the hydrogen bond between water molecules. Less energy is released when new attractions are set up between haloalkane and water molecules, as they are not as strong as the original hydrogen bond in water. As a result, solubility of haloalkanes in water is low. However, haloalkanes tends to dissolve in organic solvent because of new intermolecular attraction between haloalkane and solvent molecule have much the same strength as the one being broken in the separate haloalkane and solvent molecule. Now let's try to understand the meaning of these lines. Any molecule to be soluble in water. So the solubility in water depends on two factors. First, the molecule should be polar. So all the polar molecules are soluble in water. So molecule should be polar. Second point, if the molecule is ability to make hydrogen bond with the water, they are soluble in water. Now compare the solubility of alkyl halides in water. Let's take an example of methyl chloride. So it is CH3Cl. So when you see the molecule is polar, so molecule is polar because there is electronegativity difference between halogen and carbon. But there is no electropositive hydrogen which is directly bonded to electronegative element. That's why these molecules cannot make hydrogen bond with itself or with the water molecule. So they cannot make hydrogen bond with itself or with the water molecule. For example, if there are two chloromethane molecules are there, between two chloromethane molecule, there will be dipole-dipole interaction as the molecule is polar. So there will be dipole-dipole interaction between two chloromethane molecule. In case of water, water is a polar molecule and there is hydrogen bonding and they can make hydrogen bond with itself. So there is hydrogen bond between two water molecule. But when you mix them together, there will be new interaction will be formed. So between chloromethane CH3Cl and water molecule. So there is no hydrogen bond between these two molecules. So there is no hydrogen bond between these two molecules, but there will be dipole-dipole interaction between these two molecules. So when you compare the interaction before dissolving these molecule in water, water has hydrogen bond. But on dissolving this molecule in water, there will be no hydrogen bond. So that's why the new formed interactions are weaker as compared to before. That's why it is written here, the new attraction are set up between the haloalkane and water molecule as these are not as strong as the original hydrogen bond in water. As a result of it, solubility of haloalkane is lower in water. So that's why haloalkanes are less soluble in water. But they are more soluble in organic solvent. Because organic solvent, there is no hydrogen bonding. So there will be same intermolecular force of attraction before and after dissolving the molecule in the organic solvent. Now let's try to solve this question. Arrange each set of compound in order of increasing boiling points. First set of molecules are given: bromomethane, bromoform, chloromethane and dibromomethane. So let's draw the structure of all these molecules. First one is bromomethane. So bromomethane is CH3Br. This is bromomethane. And next one is bromoform. Bromoform is CHBr3. This is bromoform. Then chloromethane, CH3Cl. Then dibromomethane. So here it is CH2Br2. They all are one carbon molecule. So the number of carbon is same in all these molecules. You just have to compare the molecular mass or the number of halogen atoms in these molecules. Bromomethane and chloromethane, there are monohalogen compound. So when you compare the molecular mass of monohalogen compound, chloromethane have least molecular mass. It has least molecular mass. Bromomethane will have higher boiling point. Then bromoform will have highest boiling point. So this is the order of boiling point. Now come to the second question. 1 chloropropane, then isopropyl chloride, then 1 chlorobutane. So let's draw the structure of these molecules. So it is the second question, and let's draw the structure of these molecules. First one is 1 chloropropane, CH3, CH2, CH2, and it is bonded with chlorine. So this is 1 chloropropane. Now draw the structure of isopropyl chloride. So it is CH3, CH, CH3, and Cl is bonded to second position. This is isopropyl chloride. Third one is 1 chlorobutane. So here CH3, CH2, 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 and this is Br bonded to first carbon. So when you compare the molecular mass of these molecules, bromobutane have 4 carbon, so it will have highest molecular mass, so its molecular mass will be higher. So it will have highest molecular mass. So it have highest molecular mass, so it has higher van der Waals force of attraction. That's why the boiling point of bromobutane will be highest among them. Now you have to compare between these two isomers of chloropropane. Isopropyl chloride has one branch. So as we have learned before, branching decreases the boiling point. Because of the branch, there is less point of contact between the molecules, so there will be less van der Waals force of attraction between the molecules. So the molecule have more branches will have lower boiling point. So this molecule has one branch of chlorine, that's why it will have least boiling point. So when you arrange them in increasing order of boiling point, isopropyl chloride will have least boiling point. So here you can write isopropyl chloride will have least boiling point, then chloropropane, then bromobutane will have highest boiling point. In the next video, we will discuss chemical reactions. Molecule having least molecular mass will have lower boiling point. So here chloromethane will have least molecular mass. After chloromethane, bromomethane will have higher molecular mass. So the boiling point of bromomethane will be higher than that of chloromethane. Bromoform have 3 bromine and dibromomethane have 2 bromine molecules. So after bromomethane, dibromethane